All right, let's dive into a science that's pretty much hidden in plain sight, but it literally powers our entire modern world. It's this silent force working in everything from your car to the jewelry you might be wearing. And we're about to see how it all kicks off with one single, really simple idea.
So to get us started, just think about three completely different things for a second. You've got a car battery, a massive steel bridge, and a delicate gold ring. I mean, on the surface, they have absolutely nothing in common, right? Well, it turns out they share this secret connection, a core principle that actually makes all of them possible.
And the answer is a controlled flow of electrons. That's it. Seriously, this simple but incredibly powerful idea is the beating heart of a field called electrochemistry. Today, we're going to pull back the curtain and see how it acts as this invisible engine driving some of India's biggest industries.
And that's really the best way to think about it. Electrochemistry isn't just some chapter in a textbook you forgot about, it's a massive invisible engine. But unlike a normal engine that just uses brute force heat, this one is all about elegance, precision, and control.
So what is it exactly? Well, you can think of electrochemistry as a two-way street. On one hand, you can use electricity to force a chemical reaction to happen. And on the other hand, you can take a chemical reaction and use it to create electricity. It's this dual personality that makes it so unbelievably useful.
And here's what's so cool about it. The very same concepts you might vaguely remember from your high school science class, those are the exact same principles being used right now, but on a massive industrial scale. So let's connect those dots.
Does this word ring a bell? Electrolysis. You know, it's that classic classroom experiment where you stick two pieces of metal in water, run a current through it, and poof, you see bubbles. You're literally using electricity to rip water molecules apart into hydrogen and oxygen. Well, it turns out this isn't just a little demo for class. That simple idea gets scaled up, way up. Over in Odisha, the national aluminum company, NALCO, has this huge challenge. Aluminum ore is super tough to crack open. Just heating it up doesn't work. So what do? They use something called the Hall-Héroult process, which is basically just electrolysis on a colossal scale. They blast it with insane amounts of current to get 99.5% pure molten aluminum. It's the school experiment, totally supercharged.
Okay, now let's flip the coin. Instead of using electricity to do something, what if we use chemistry to make electricity? Well, that's the job of a galvanic cell. Inside one of these, a chemical reaction just happens on its own, and as it does, it releases energy that we can capture as electricity. This, right here, is the fundamental principle behind every single battery you've ever used.
And this quote shows just how high stakes this technology gets. On ISRO's spacecraft, fuel cells, which are just a fancy type of galvanic cell, are literal life support. They don't just provide the electricity to run the ship's systems, their only byproduct is pure, drinkable water for the astronauts. I mean, in space, you can't have an off day. This is the tech they trust with their lives.
So we've seen how electrochemistry can build materials and generate power. But that same flow of electrons can also be a powerful problem solver. It helps us fight one of the most stubborn and expensive enemies in all of industry, rust, or, to be more technical, corrosion.
To get how this works, you have to know about something called the electrochemical series. Honestly, the easiest way to think about it is like a scoreboard for metals. It just ranks them based on how badly they want to give away their electrons, which is just a fancy way of saying how easily they rust. So let's look at a quick comparison. You've got zinc and you've got iron. Zinc is way lower on that scoreboard than iron is. That means it's much more eager to react and give up its electrons. It wants to corrode way more than iron does. And this simple fact is the secret to protecting literally trillions of dollars worth of infrastructure.
So how do we use that?
Well, it's actually pretty clever. Companies like JSW Steel use a process called galvanization. They just coat their steel with a thin layer of zinc. The moment any moisture hits it, a tiny electrochemical reaction starts. But, and here's the trick, because zinc is so much more reactive, it basically shoves the iron out of the way and corrodes first. It literally sacrifices itself to protect the steel underneath. It's a bodyguard for metal.
And this isn't just for sheets of metal. The Indian Oil Corporation protects its huge network of underground pipelines the exact same way. They attach these big blocks of magnesium, another metal that's even more reactive than zinc, directly to the steel pipes. Those magnesium blocks slowly corrode away over many years, saving the pipeline from what would be a disastrous and costly leak.
But electrochemistry isn't just about big, powerful applications and protection.
Its other superpower is almost unbelievable precision. We're talking about controlling chemical reactions right down to the atom. This amazing precision comes from a set of rules called Faraday's laws. Now, don't worry about the math. Just think of them as the ultimate chemical recipe. They tell you with absolute certainty that if you use an exact amount of electricity for an exact amount of time, you will create an exact amount of a substance. No guesswork, no about, just exact.
And here is a perfect, beautiful example. How does Titan's Tanishq brand get that flawless, perfectly even gold finish on a piece of jewelry? Electroplating. They make the jewelry one of the electrodes in a bath of gold solution. Then, using Faraday's laws, they calculate precisely how much current they need and for exactly how long to deposit a layer of gold that is perfect down to the micron. It is pure science creating pure luxury.
Okay, so luxury is one thing, but let's raise the stakes even higher. Because in the pharmaceutical world, precision isn't about looking good, it's about safety. When you're making medicine, close enough can be incredibly dangerous. You need absolute certainty.
So how do you get that kind of certainty? How do you measure something like the acidity, the pH, of a new drug with the kind of accuracy you need to know without a doubt that it's safe for people to take? You use another brilliant electrochemical tool, the Nernst equation. This formula is basically the brain inside every modern pH meter. It's so clever, it can take a tiny, almost invisible voltage measurement and translate it directly into a super precise chemical concentration. This is exactly how companies like Sun Pharma can guarantee the safety and stability of their products.
So, what a journey, right? We've gone from a basic concept in a classroom all the way to massive assembly lines, protective coatings that save pipelines, and precision instruments that ensure our medicine is safe. But the story is definitely not over. This really brings it all home. Those foundational ideas, like redox reactions, are what power everything from ISRO's fuel cells to the batteries in your phone. Those intermediate concepts, like electrode potentials, are what allow a piece of zinc to act as a bodyguard for steel, and the advanced tools, like the Nernst equation, give us the incredible precision we need. The link from simple theory to industrial power is direct, and it is undeniable. And the next chapter of this incredible story is being written right now, as we speak. The solutions to some of our planet's biggest challenges, things like the transition to electric vehicles, the production of clean, green hydrogen, and creating advanced sensors to protect our environment. All of it depends on us mastering electrochemistry. So it leaves us with one final big thought. We've seen how a simple, controlled flow of electrons can build our world, power our lives, protect our most critical infrastructure, and even keep us safe. If it can do all of that today, what new, incredible problems are we going to command it to solve for us tomorrow?